Then we are going to look at the various types of relays here based on their operation. So the ones we saw above was the various types of relays based on their construction. Yeah. So based on their operations here, because the operation here is particularly get on the purpose of which it is used in the transmission line protection. So we have the overcurrent relay, the distance relay, the directional relay, differential relay, and so on. So these are the main types which have been highlighted. The overcurrent relay here has two settings, which the time setting and the clock setting, and it is used to protect the line against an overcurrent, as the name states, overcurrent relay. And it has a single input which comes from what the current transformer. Since we are utilizing current in this aspect of the overcurrent relay protection scheme, the input is from the current transformer. So the voltage transformer is not used here for the overcurrent relay protection scheme. It utilizes only the current transformer. So when the input is being set, the overcurrent relay has to do what? Compare this input current to the current that has been set using what? The clock setting or the pickup current. Any of the names, they are just represent either the British or American standard. It has been noted as well in the course. So it compares the input current with the current that has been set to know whether the power system or the line is operating at normal condition or at faulty condition. And it is also able to give an appropriate time in order to send the tripping command to the circuit breaker. So the time here is being configured or set using what? The time setting. And we have various time settings based on the amount of current or the fault levels, be it instantaneous time, definite time, and so on and so forth. For instantaneous time relays, we'll see that we'll see that no matter the level of the fault, that is, no matter the level of the faulty current, the instantaneous relay will give a tripping command within an operating time of 0.1 seconds, whether the faulty current is as small as what or it is very, very high. It gives that tripping command within that specified time of less than 3 cycles, which is approximately equals to 0.1 second. So that's the instantaneous relay. Then we also have the definite time relay. This definite time relay, it is similar to the instantaneous relay but different in the sense that you can configure or you can define the time to which it should give that tripping action. But once you have configured this time, it trips for every amount of fault, be it a smaller faulty current or a larger faulty current, it trips within that prescribed time which you have defined. So the instantaneous relay, the time has been defined at 0.1 second. So with a definite time, that time can be changed to might be 0.3 seconds or whatsoever time you wish to change. But when it has been configured as such, the tripping occurs within that defined time for any amount of fault, whether the fault is of thousands of amperes or whatsoever, it trips within that same time which has been set. Okay, then we have the inverse time overcurrent relay. The inverse time overcurrent relay has here a decay curve, characteristic curve of time against current. So in this case, the current relay is a little bit more biased in the sense that it doesn't uh, for various amount of faulty current, it does not trip within the same time, right? For example, from the curve we see here that if we have a current IN, a faulty current IN, which is very, very much less, the tripping time will be higher. Meanwhile, when the fault level increases, for example, let's look at 10 times that IN or nominal fault current, we see that the time becomes very, very much small, going towards more an instantaneous time of probably the instantaneous relay, but the time becomes very, very much small. Okay, so we have different types of characteristics of the inverse time. We have the moderately inverse, the inverse, and the extremely inverse characteristics. So it is defined based on the level of the decaying level of the inverse curve, characteristic curve. Then we have mixed curves. That means these three characteristic curves that have been defined above can be mixed or intertwined or combined. For example, we have the inverse time and the instantaneous time characteristic curve. So we have relays that can operate using inverse time and instantaneous time, depending on the amount of fault, right? You also have that of the inverse time and the finite time. Then you also have the inverse time, the instant plus instantaneous plus the finite time. So those are the various types of characteristic curves which you have for the various relays, over current relays. So here is the British standard and American standard of the various uh, names that are used in setting the relays. We have the plug setting in the British standards, meanwhile in the American standard is called the current tap setting. The British standard calls the time multiplier setting, uh, meanwhile the American standard will call it the time dial setting, right? These are the various settings that are used in configuring the overcurrent relay. Then we have the American standard curves for the various types of overcurrent relay. We have the overcurrent relay 6, overcurrent relay 7, 8, 9, 11, which are represented on the curve in this figure, which are represented in this figure. The figure shows the time in seconds on the vertical axis and with respect to the multiples of the peak current on the pickup current, sorry, on the horizontal axis. Then here we have the time of operation. Here, time of operation for the various characteristic curves of the various types of overcurrent relay. Here are the various types which have been broken down. For example, this is that of the CO7 overcurrent relay 7, right? So here's a time deal setting. Here's a time deal setting. So you can have different time deals, time deal 1, time deal 2, time deal 3, and so on and so forth. So you can use any of these time deals and with respect to that, the operating time can be defined and the multiples of the tap current of the tap setting or plug setting on the vertical axis. So with respect to this, you can deduce one parameter if you have the other. Even while doing some calculations, these curves will help you in order to have the other parameters effectively. Okay, this is that of the CO8 relay. It's still the same characteristics, the same parameters, sorry, but the curves are a little bit different. And so you have also the British standard. Here's the British standard curves. So you see the operating time versus the multiples of plug setting. So the time multiplier setting here, or the time deal setting, which the American will call a time deal setting, here are they. You see, for example, for the curve 1 is Z as the arrow shows. For curve 0.3 time deal or time multiplier setting 0.3, here's a curve. and so on and so forth. So if you are using a particular time deal, for example, if I'm using time deal 0.3 and the uh, multiple of clock uh, or the clock setting is probably at 10, you see that you have to extrapolate to when it caused that time deal of 0.3. From there now you extrapolate vertically, sorry, horizontally to get what the operating time of that relay for that amount of current. Okay, so we can as well have for a time multiplier setting of 1, a curve for time multiplier setting of 1. This is it, right? Here you don't have time multiplier setting for the other might be values 0.1 to 0.2 to 0.3, 0.4, and so on and so forth. As we saw up here, here was varying from 0.1 to 1. That is time multiplier setting of 0.1 to 1. So you have these different curves. But you can simply have a curve with just a single time multiplier setting of probably 1, right? So with respect to these can be given even while designing a system of which probably you want to use another time multiplier setting, but of which you have just this time multiplier setting of 1, you can still use it, but you have to do some logics in order to deduce for the required time multiplier setting which you are to use. Even in questions, if a question is given to you, you can still use time multiplier setting of 1 and apply it to the required time multiplier setting which you need or which you wish to use. Okay, those this curve as well, that inverse curve can be represented on a logarithmic scale as such. So instead of giving you that inverse curve, a logarithmic scale can be given to you as such. It's still the same, but now this logarithmic scale is for time multiplier setting of 1. So if, for example, you're using a different time multiplier setting of probably let's say 0.6 or 0.3, but you're given a scale of time multiplier setting of 1, you can still be used, it is still useful. You still use it, but you have to do some logics, right, in order to attribute the time multiplier setting. For example, I can say a time multiplier setting of 1, we have a pickup current of probably this or a tripping time of 7. That means that a time multiplier setting of 0.6, the tripping time will be, you deduce what that might be, that 0 point something times 7 divided by 1. So you give you that tripping time. So you can see it in the questions below. And this operating time here can also be determined not only from the curve, but it can as well be determined from the equations. These equations here are the equations relating to those curves. So you have it for the American standard, which is given as such: the time deal times 5.95 divided by m squared minus 1, where m is what? This the clock multiplier setting, which is the current fed by the uh, current transformer to the relay, that is I relay, divided by the pickup current of the relay. Same thing with the British standard, you have the operating time given as such, where TMS is the time multiplier setting here. Then we have IF as the faulty current. CTR is the current transformation ratio, and then PS is the plug setting. Yeah, so that's it for the overcurrent relay. Okay, so it's essential to note that that plug setting multiplier was also stated up here. The plug setting multiplier is the current fed by the current transformer to the inputs of the relay. That's what is called here I relay, divided by the plug setting of the uh, relay. For example, a relay might be given with plug setting of 5, right? So utilize it to have the plug multiplier setting if you know the input current fed by the current transformer to the relay. Here is a figure of how the relay is, or the overcurrent relay is here. So you see how its interface is. So you see the buttons on it, which it can be manipulated and can be set appropriately. Okay, so we are going to look at the distance relay. The distance relay here normally uses the impedance to measures the line impedance, it measures the line impedance to actually detect whether there is a fault or not, because the line normally has an impedance, and during a fault the impedance of the line will certainly change during faulty conditions. So it's able to determine the impedance with respect to the point of fault and know if there is a fault or not. And it can as well give a prediction of what the distance to which the fault has occurred, so it is also appropriately used in fault location. So you can appropriately, or you can predict the location of the fault depending on the distance, because using the impedance measured on the line, you can actually determine the area in which the fault is located. So you can read much more of that. Here's the relay characteristic for the distance relay curves. You see here this zone, which is empty, shows the zone in which the relay would operate. If the impedance is above this zone, shows that the relay will not operate. That means it is at normal conditions. Okay, we have different types of distance relays, not only the impedance, the impedance relay. We have the admittance relay and the reactance relay. So they utilize the various parameters of admittance or reactance in order to detect the faults. So the advantages of the distance relay have been enumerated here, right? And there's also what we call the pilot scheme of protection. We are going to look at the various schemes of protection down. Okay, in this next section, the various types of protection schemes for the uh, overcurrent relay, for the distance relay, for the differential relay, and so on. The pilot protection. Okay.